Welcome back, and let's write some more neat code today. So today let's solve binary tree maximum path sum. And yes, this is another problem from the blind 75 LeetCode list. So this is a list of 75 common LeetCode questions, and today we're going to be solving this tree question, binary tree maximum path sum. The link to this spreadsheet will be in the description if you do want to take a look. And I think I've almost done all of the problems that I wanted to do from this list, nearly all of them so far. So a path is defined in a binary tree as being a sequence of nodes where each pair of adjacent nodes in the sequence has a edge connecting them, and a node can only appear in the sequence at most once, and the path sum of that path is defined as being the sum of all the nodes' values in that path. So for example, in this example, we're given a tree, and the path is basically going like this, right? You see how, we have a node, we go here, and then we go here, right? This counts as a path, right? Even though from here we're technically splitting, we're going left and right, this is still a sequence of nodes, right? It could be read like in any direction, but it's still like a sequence. And then when you take that path, you basically get 1 plus 2 plus 3, so that's going to be the output. Now, of course, in this problem, we can actually have negative values. So for example, this 2 could be -2. So then what would be the maximum path sum then? Well, we don't want to add negative values. That won't increase our total. So in this case, we're going to go from here to here, right? This is going to be our path, 1 plus 3, and then we would return 4. Now, what happens if this value was a -1 instead, right? Now, we could just take 3 by itself, that counts as a path, or we could take 2 by itself, that counts as a path, or we could still take that same path, which would give us 2 minus 1 plus 3, which gives us 4, and that is actually the max once again. So it's possible that negative values could still be included in the output. So you might think, well, what if we have a tree of all positive values like this one? Can we just take every single node, like basically like this, and call it a path? And just add every value together? Well, no. And the reason is because if we had this structure, right, this isn't really a path, because how would you traverse it, right? We could start here, then go this way, then go down, but then here we have to make a split. We can't go in 2 directions at once. That doesn't count as a path. So basically what we realize is, as we look at this example, is that if we're starting at a node, we can only split once, right? Like if we're here, we can split in 2 directions, right? We can include a path from here, from the left side, and then we can also go here, right? And if we get to this portion, right, we already had a split up above, so we can't split twice, right? Because then it's no longer a path. So we can only choose one of these nodes. We would obviously choose the bigger one, that's a 5. Right, so take a look. What would the sum be if we ended up splitting from here? This is obviously the max we could create. What is the total? It's 1 plus 2 plus 3 plus 5, which is going to be 11. Now, we're going to try it multiple ways, right? It's possible maybe there could be a split over here. Of course, this doesn't have any children, so the most we could get doing that would just be a 2. But what about over here? What if we ended up splitting from here? So we took the left and the right from here. We'd get a 4 and we'd get a 5. Now, if we did do that, notice how this is going to be the topmost node. So whenever we split from a node, we can't really get any of its parents or anything like that. So in this case, what is the sum of this path? Well, it's going to be 4 plus 3 plus 5, which is going to give us 12. 12 is greater than the 11 that we had previously, so this is going to be the max path sum. So you can tell that a brute force approach would be for every single node, consider it being the topmost node, and then from the left subtree, basically find what's the maximum path we could create in the left subtree if we never split. So we can't include both left and right, and then do the same for the right side, right? And if we sort of do it recursively, we can eliminate repeated work. So suppose we're given that same tree. We're going to start at the root like normal, right? So from here, we want to know what's the max path sum we could do from here if we split from this position, right, going left and right. Now, Why start at the root when we could solve the subproblem first and possibly use that subproblem in the result at the root position? So we're going to leverage that idea, a depth first search idea, just like usual with tree problems. And using that, we're going to end up getting a linear time solution, and it's just going to depend on the return value of our recursive function. So we're going to start at the root, and now we're going to go left, right? We want to know what's the maximum path we can get from the left subtree if we never end up splitting. So in this case, it's pretty simple because it doesn't have a left child or a right child, right? So we don't even end up having to split, and we get a sum of 2 from this spot, right? And even if we were splitting from here, we would get a total of 2 so far. So what we'll say is, so far the max path we've gotten so far is 2, right? Now, we still want to know what's the max we can get from this position, so what we're going to do is now go to the right tree. So recursively, now we're going to ask the question down here, what's the max path sum we can get if we ran it through this position and we ended up splitting left and right? And by the way, our result so far is going to be 2. That's the maximum path so far that we've gotten. So from here, we're going to, since we're trying to, again, find what's the max we can get splitting from here, we're going to go recursive, and we're going to do that for the left subtree and the right subtree. So we're getting that same base case here, right? With this left subtree, if we tried to split from here, the max path we'd get is 4 because it doesn't even have any children, right? So let's keep track of that. The max path we could get from here is 4. Now, if we didn't split here, we'd also get that same value of 4. And that's what I'm marking here. Next to each node, I'm marking what's the max we could have gotten if we did not split. I know it's a little confusing, and it'll make more sense once I actually finish the rest of this example. And so from over here, now we do have what's the max we'd get from the left path without splitting. It's 4, but now we just want to do that for the right side. Once again, it's that same base case, right? So what's the max we could get running through here if we never split? It would be 5. It doesn't have any children, so we couldn't split even if we wanted to. So now we're at this node once again. We have computed the left and right subproblems. Now from this node, we're going to be computing 2 different values. By the way, our result right now would actually be 5 because that's what we've gotten so far. So from this position, I'm computing 2 values. I want to know what's the maximum sum we could get with a path running from here if we are allowed to split. So we are allowed to go right and we are allowed to go left. So what would the total of that be? Well, of course, we would just take, okay, what's the max we could get from the left subtree without splitting, right? Because we can't split again. If we already split up here, we don't want to split again here. So what's the max we could get from here if we never split? Well, it would be 4, right? And once again, what's the max we could get from here if we never split? It would be 5. So up here, I'm going to take 3 plus 4 plus 5 and say this is the max path running through here if we are allowed to split. Now, this isn't the value that I'm going to return to the parent. The reason I computed this value is so I can potentially update the result, right? And we are going to update the result because this is 12. So far, our result is 5. So we can say that our new result now is going to be 12. Now, what's the value I want to return up to my parent? Remember, what this guy wanted to compute was what's the max it could have if it was allowed to split to the left and it was allowed to split to the right. So from here on, we don't want to split twice. So the question I have for this node when we're returning up to our parent is what's the max I could get running through here if we are not allowed to split? So how am I going to get that? Well, I can take this 3 and add it, but then I have to look at my left subtree and my right subtree and take the max of both of these, right? I have to take the max of them. I can't choose both, so I have to choose one of them. I'm going to take the maximum, which is going to be 5. So I'm going to say 3 plus 8, that's going to be the value that we return. So notice how for each node I'm marking what's the return value from that node going to be. So it's going to be 8 in this case. So then when I return back up to the root, I'm going to say, okay, from here, what's the max path we could get? Well, I'm going to take the node itself, 1, take the left, which is 2, and take the right, which is this path, right? Notice how we don't split. It's going to be an 8, which is going to give us 11. Now, that's not bigger than our result, right? So we actually don't update the result in this case. And of course, this is the root node, so it's not going to end up returning to its parent. But what if it did have a parent? What would it return? Well, we would take 1 and then add it to the max of the left or the right. Of course, the right is an 8. This is the path, so we'd say 1 plus 8 is going to be 9. 9 is what we would return to our parent. That's the max path we can get from here without splitting. What would that path look like? Well, of course, it would just be this, right? Notice how this is a path. It never splits. So that is the main idea for this problem. There's one last quick thing I want to go over. So the return value, of course, is going to be for every node, what's the max path without splitting, and we are going to still calculate what's the max path with splitting and use that to actually update our result. We're going to keep this as a global variable because it just makes the code easier, but it is possible to solve this problem without using this global variable. And by the way, if you've been noticing, we're only going to be looking at each node once, so that's going to be a time complexity of big O of n. The memory complexity, of course, is going to be the height of the tree, which is usually log n if it's a balanced tree. But one last case, remember this tree could have negative numbers. So for example, let's say this was a -4 and this was a -5. So then from this left subtree, we would return a -4, and from this, we would return a -5. So then, when we're actually computing, okay, what's the max path that could run through here? And let's say we're doing it for the one that we can't split, right? Where we don't split. So we either choose the left or the right. And as I mentioned, how we're doing it is we're just taking the max of the two, right? So in this case, we would take the max of -4 and the max of -5, right? And of course, we'd say the max is -4. So then when we're up here, what we would end up computing is 3 plus -4, which is going to give us -1, right? -1. So what we would say is, okay, the max we could get here without splitting is going to be -1. But that's not actually the case, right? Because to get the maximum path sum from here where we're not allowed to split, it doesn't necessarily mean we have to include the children, right? They're optional. We could actually choose to not include either of these, and that's what we would want to do because they're both negative anyway. Why would we want to include some negative numbers? So when we're actually taking the max of the two, we're actually going to take the max of 3 values. We're going to take the max of the left, right, and potentially 0, because if we just add 0 to it, this will stay the same. So those are the
Mm. Ah, um, Sure. Rest. Stand.
The key ideas I wanted to go over, I think that is enough for us to dive into the code to solve this optimally. So like I said, we're going to have a global variable for the result, and initially we're just going to set that to the whatever value happens to be at the root. So the reason I'm making it a list is because that'll make it so that we can modify it within the recursive function a little bit easier. So we're going to have a recursive DFS. We're going to pass in whatever root node we're traversing, and that's really all we have to pass in. So now the base case is that if we don't have a root, like if the node is null, in that case, what we're going to return is just 0. That means we're not going to be adding anything. And so we're going to be returning, I just added a comment, we're going to return from this function the max path sum without splitting. So we want to get the max path sum. So of course we have to do this recursively. So let's get the left max, and we can do that recursively. Just pass in root.left. If it's null, of course, that's just going to return 0. We're also going to get the right max, passing in root.right. So the first thing I'm going to do is compute the max path sum with a split from this root node. So basically what I'm going to do is I'm going to take the root dot value and add it with the left max and the right max, right? Because we are splitting from this root node. Now, of course, these left and right maxes could be negative. So what I'm actually going to do before that is update them. So we're going to set left max equal to the max of itself and 0. And do the exact same thing with the right max. So it's going to be set to the max of itself plus 0. So here we're going to be computing the max path running through here. So we're going to take the root value, the left max, and the right max, add them together. Now this could potentially be our new result. So let's see if it actually is. So result at position 0 is going to be set to the max of itself, or this value that we just computed. So this is the part where we're actually computing what could actually be the updated result. Now, what the return value, remember, of this function is not going to be the same as this. The return value is going to be what we compute without splitting. So the return value is going to be return root.val plus whatever the max of the left max and right max is, right? Because we can't choose both, because if we choose both, that means that we're splitting. And so that's actually the entire function, right? You can see when we handle the recursive case well, and we take the max of it and 0, then we really just have two main computations we're doing, right? The max path sum with a split and the max path sum without a split. Of course, this one is going to be the return value, because we can't choose 0 is going to be 0. And do the exact same thing with the right max. So it's going to be set to the max of itself plus 0. So here we're going to be computing the max path running through here. So we're going to take the root value, the left max, and the right max, add them together. Now this could potentially be our new result. So let's see if it actually is. So result at position 0 is going to be set to the max of itself, or this value that we just computed. So this is the part where we're actually computing what could actually be the updated result. Now, what the return value, remember, of this function is not going to be the same as this. The return value is going to be what we compute without splitting. So the return value is going to be return root.val plus whatever the max of the left max and right max is, right? Because we can't choose both, because if we choose both, that means that we're splitting. And so that's actually the entire function, right? You can see when we handle the recursive case well and we take the max of it and 0, then we really just have two main computations we're doing, right? The max path sum with a split and the max path sum without a split. Of course, this one is going to be the return value, and after we're done with that, all we do is call our DFS passing in the root, and then that will update our global variable up above, which is the result. Then we can go ahead and return that result, and that is the entire function. I'll run it, and you can see that it does.
Oh, I don't know when the sun doesn't fall in love again.
Hey, whatever the max, hey, left max, hey, hey everyone, dated result, hey, plus, hey, dated result. Now what the return value, remember, of this function is not going to be the same as this. The return value is going to be what we compute without splitting. So the return value is going to be return root.val plus whatever the max of the left max and right max is, right? Because we can't choose both, because if we choose both, that means that we're splitting. And so that's actually the entire function, right? You can see when we handle the recursive case well and we take the max of it and 0, then we really just have two main computations we're doing, right? The max path sum, see that it does work now.
Rain's over Africa.